Hello, everyone. I'm Bob. I'm working with Quantinuum. I'm chief scientist there. Uh, Unfortunately, I can't make it for when this keynote will be streamed, but Ellen asked me to record it because of that reason. I also have a group office in Oxford, and there we work at the intersection of quantum and AI in a somewhat different way than most people have been working on that intersection, and I'll comment on that in this talk. Let's just start. So the context here is that large language models, such as ChatGPT, have deep-seated and systematic problems. As we all know, we don't know how they work, and that's where the call from for interpretability has come from. Like people want, like machine learning and all of that AI to be interpretable for all the obvious reasons. Because the behavior can't be controlled, predicted, anything. This is like what lots of people are talking about. One thing people don't usually mention is where are we going to go next after we have done this thing? If you look at the history of science and technology, then we know that the lack of understanding typically results in a dead end, despite how successful something can be for a while. One example is the Babylonians. Another example is the model of Ptolemy for like planetary movement and ship navigation. So this is one context. We actually want to make AI a little bit more understandable in different terms. Now there is another bit of context, and this specifically relates to what people have been doing in quantum machine learning and quantum AI. Quantum machine learning algorithms require training at scale for obvious reasons. You can't just dump data in a quantum computer, and this is part of the nature of a quantum computer or how we understand it today. There are no theoretical results assuring that there is efficient ways of training. If you do what I would call vanilla quantum machine learning, which is what people have been doing for a long time. Not everybody, but a lot of people have been doing what I would refer to as vanilla quantum machine learning. This is a serious problem for the field of quantum machine learning as a whole, which generally has shrunk enormously because of this problem. The thing is, if you can't prove theoretically that you can train at scale, then you have to show it experimentally. But at the moment, the machines aren't big enough. So kind of the activity is to some extent put on hold. What is the crux to our solution? The crux to our solution starts like a long time ago with John von Neumann. So John von Neumann is the father of the quantum mechanical formalism. He publicized this in a book in 1932, and in 1935 he denounced his own quantum mechanical formalism and said there should be a new one. I've been working for a very long time on this, starting in the late 90s, and a lot of that work resulted in more than one book, but this is the last book, Quantum in Pictures. And this is entirely new quantum formalism we find there. You don't need any mathematical background. So for people not coming from the typical university education that you need to learn quantum, you can go here. And it's quite different from, it's totally different from the usual quantum mechanical formalism. Now, we did an experiment to show the value of this formalism, as this Garden article, and this is basically on the back of this experiment that we did. So basically, what did we do? We taught high school students, UK high school students, which were randomly selected, the equivalent of an Oxford postgraduate course. So we followed the format of an Oxford University postgraduate course. And then at the end, we asked them to do an exam which entirely consisted of Oxford University postgraduate questions in quantum, which had been done before. But the big difference is we did it all in this language, not the usual quantum formalism. As a result, the teenagers, the high school students, basically outperformed on average what Oxford University's postgraduate university students would do. If you want to get a more extensive talk specifically on this topic, there is like a Royal Institution talk, which I gave like a few weeks, months ago. And so I go into much more detail about this. Now, at the core of all of this, it's not just pictures to make things look nice. There's actually the concept of compositionality, and which is the principle that underpins functionality of all our current IT. Like everything, your smartphones, everything is based, whatever is in there is based on the concept of compositionality, which initially came from linguistics, and is typically attributed to Frege. Now, the notion of compositionality which we need today, if you're going to look at language in the way it's today like used, and also at quantum, you kind of need a different notion. In this paper, I talk about the problems surrounding traditional notion of compositionality. Can't go into that here. And then we base specifically in the case of like explainable AI, we actually came up with a definition of compositional interpretability. In this paper, it's still a proposal. We are a little bit further than that now. So now we've got a proper notion of compositional interpretability for explainable AI. And that's something I'll be referring to in this presentation. Now, rather than explaining what it is, here is a counterexample. You see a picture of a bird, you see a picture of a neural network. That neural network is compositional in the sense that it's composed out of like nodes. But of course, composition of nodes has nothing to do with the structure of the bird per se. And so it's not a reflection of what it's talking about. Compositional interpretability wants a relation to between the model and the phenomenon that you consider, which is what people in science have always done, by the way. This is totally standard practice. So what we are working on mainly in the space of language, and I can't go into that, but this actually also goes well beyond language to spatial representation, cognitive features, many other things. But so I'll focus on language here, is something text circuits. So to give a bit of history there, like people who start seriously thinking about a structure of language go back like to the 30s and the 40s. I've got Chomsky here and Jim Lambeck. Jim Lambeck is responsible for like the proper mathematization of the structure of language. And so basically, the way you can think of this is they identified some compositional structure in the phenomenon of language. In their case, it was mainly the structure of sentence and grammar. We did some work based on that, which started like a very long time ago. Like the paper on the top left goes back to 2008. We worked to 2006, 2007. And so we got a software tool like which is called Lambeck to deal with that. And so when we're initially starting this, we basically presented this as a quantum-inspired theory of language. Of course, because it's quantum-inspired, it's also sort of quantum compatible in a very strong way. We had some results that with this model, we would obtain quantum advantage if we stick it on a quantum computer. That's the bottom left. And we, for the first time experimentally, did some question answering using this model, like early 2020, and we publicized this in late 2020. That's not really what I want to focus on now. This is basically like traditional old-fashioned grammar structures a la Lambeck and Chomsky. So the text structures, which I think are much better suitable for AI applications because they get rid of a lot of the bureaucracy of language while maintaining the essence of meaning and the structure of meaning. The structure of meaning is not essentially necessarily the same as the structure of language or grammar as we write. I think it lives at a much more higher level. It should be language neutral and things like that. It should be neutral between representation, be it language or visual representations. And that's what these things are. So these are these text circuits, and you should think of this as a new compositional structure within language that we identified. Just to give an idea how this works, here you got a little text: Alex meets Bo, Bo marries Chris, Alex kicks Bo. So a natural representation of this is like you got three agents, Alex, Bo, and Chris. And if you want to think of them as quantum systems, then of course the meeting of Alex and Bo is like entangling these two systems. And then Bo marries Chris is definitely some form of entanglement, a different form than meeting, so it will be a different kind of entanglement. And then of course when Alex gets upset and kicks Bo, that's yet another form of entanglement. So there's different forms of entanglements here going on, but I think this representation of a circuit is very natural, and you can do this for all of English, you can do this for any language. And one of the nice things is whatever language you use, the circuits will always become the same. They don't care about which language you speak. They also don't care about your writing style, whether you want long sentences or short sentences, you always end up with the same circuits. Now, a theorem. This is a theorem which we haven't publicized yet, but which I think is very important, that under the assumptions of what we call compositional interpretability, which means that the compositional structure in the phenomenon is also reflected in the model you deal with it, and that you want learnability, so to apply like modern methods of learning something, then text is what we call effectively quantum shaped. What does it mean? That you actually end up with a quantum model, like which the same quantum mechanical model that you would describe like quantum processes with. There's one difference. I'm not going to go into details, but essentially you end up in a similar situation. So the proof actually is in a book, not the book I wrote, like Picture in Quantum Processes, which also goes through all these diagrams for quantum, and that's where actually you find the whole proof of this. Now we did some work specifically on seeing how these text circuits would behave on a quantum computer and which advantage you could get from it. So with the assumptions I just said, that you want compositional interpretability and that you want to be able to learn things, like to train and stuff like that, there is like a potential exponential advantage for doing a task like question answering on a quantum computer for text. So under these assumptions I give, you can get exponential quantum advantage potentially. This is theory. I mean, I'm not going to, so this is the exact statement. I'm probably I should go into details here. We did experiments too. So we implemented this on our own hardware, on our own Quantinuum hardware, which is developed in Colorado, and we showed scalability. I'll explain in what way. And we showed quite a few other very nice features. Let's just go through them now. So of course, interpretability is one feature. I already explained that. So another feature is called compositional generalization. What this basically means, in short, is that you can train small, thanks to the compositional structure. You can train small and test large without loss of like quality of the results. So we show that, and this really thanks to the structure. Now in the case of quantum, this actually means that you can train classically. You don't need a quantum computer for training because it's small enough. Test quantumly. So you test where classical computers can't deal with it anymore. For example, because of the exponential advantage I mentioned earlier. Another feature we showed is that for the particular tasks we were doing here, which is specifically for these text circuits, that if you try to make ChatGPT do the same tasks, it's pretty bad at it. So can't go into details again, like, but the sort of vocabulary we were using is like somebody following somebody, that person following somebody else, that person following them, somebody turns around, and then you ask questions about who's walking in the same direction. So I mean, when we started this work, it was still ChatGPT 3.5. It was horrible at it. 4 was better. 4 was better, but still failed. So it's just a matter of upscaling your experiments a little bit, and then it still fails at something that we were doing very well at, even on a quantum computer, despite how small they are now. So okay, so you can read about this in the paper. I don't have to go into detail. So we have a software which is called Lambec, which implements all this stuff I'm talking about, which means you can actually work with language, with sentences, and now text. It's really, we haven't done an official statement yet as a company, but the new software is actually out there, the new version of Lambec, which allows you to take text and turn it into the circuits I'm talking about. Right. Something else we care about, like at Quantinuum, is like, and of course the name of this group includes sustainability. Could this all lead to some kind of energy efficiency? Well, I mean, first obvious answer is the paper the experiment paper I was just talking about. The fact that you can train much smaller thanks to the structure obviously save you some energy. That's obvious. That's independent of classical and quantum a priori. It saves you some energy by putting in the structure. That's clear. That's something we showed. Now, specifically about quantum hardware, our hardware people in Colorado also care a lot about that, and they've done some experiments, and specifically for a task which is called random circuit sampling with our machines, we got like some 30,000 time more efficiency as like previous kind of experiments. So, I mean, as you see, I put a question mark there because there is no rock solid evidence that this will happen, but there are some indications that quantum computing could even lead to energy efficiency. Although one should be careful at this point to make like exact statements there, but it's clearly something to look into. Okay, I'm going to end with this one. Maybe I should share the slides, I don't know. But okay, thank you for listening.